Section 3.4 Composition of Functions. In this function, you're going to learn how to combine functions using algebraic operations. You're going to create a new function by composition of functions, and then you're going to evaluate composition of functions. Here is a warm-up activity. Find the domain of the following functions. So if you have f of x is equal to square root of 2x plus 6, in order to figure out the domain, you're going to set the radicand greater than or equal to 0, solve the inequality, and the answer is going to be your domain. So 2x plus 6 is greater than or equal to 0. If you want to solve, we're going to subtract 6 from both sides. So we'll end up with 2x is greater than or equal to negative 6. Now divide both sides by 2. You will have x is greater than or equal to negative 3, which means the domain is from negative 3 to positive infinity. We're going to find the domain of the function f of x equals 1 over x plus 2 plus 3. So in order to find the domain, when you have a denominator, you're going to set the denominator not equal to 0 and solve, and then eliminate that point from your domain. So in this case, we're going to subtract 3 from both sides of the equation. You will end up with x is not equal to negative 3, which means we need to eliminate that from our domain. So following this method of graphing it on the number line and then excluding it with a circle, you will end up with this interval union. That interval is going to be the domain, which is basically from negative infinity to negative 3, union from negative 3 to positive infinity. And then given the function f of x equals x squared minus x minus 2, we're going to find f of negative 2. So the best way to do that is to remove all of the x's and replace them with placeholders and then replace the number inside. So in this case, we have negative 2 squared, which is 4, minus negative 2, that is plus 4, minus 2. 4 plus 4 is 8, minus 2 is 6. So the final answer is 6, or f of negative 2 is equal to 6. Composition of functions. Suppose we want to calculate how much it costs to heat a house on a particular day of the year. The cost to heat a house will depend on the average daily temperature. And in turn, the average daily temperature is going to depend on a particular day of the year. For example, days in January are different from days in February and March and April and etc. Notice how we have just defined two relationships. The cost depends on the temperature. So that is the first relationship, and the temperature depends on the day. The function c of t gives the cost of heating a house for a given average daily temperature T, degrees Celsius. The function t of d gives the average daily temperature on day d of the year. For any given day, the cost is going to be c of t of d. That means the cost depends on the temperature, which in turn depends on the day of the year. So the cost depends on the temperature, and the temperature depends on the day of the year. For example, we could evaluate T of 5 to determine the average daily temperature on the 5th day of the year. Then we could evaluate the cost at that temperature. We write the cost when C of T of 5. By combining these two relationships into one function, we have performed function composition, which is the focus of this section. But before that, let's combine function using algebraic operations. So algebraic operations will do exactly what you expect them to do, which is basically if you're adding two functions together, you're going to add the functions together. Like terms will be added together and etc. So function composition is one way to combine existing functions. Another way to carry out the usual algebraic operations on functions such as addition, subtraction, multiplication, and division is when you add two functions together. So if you write f plus g of x, or just f plus g sometimes, without the x just indicates that the variable is x. This basically means f of x plus g of x. So you're going to add the functions together. Similarly, if you have subtraction, you're going to say f minus g of x, or just f minus g, is f of x minus g of x. And then don't forget to distribute the negative inside if there is, if the second function is more than one expression. And then if you have f times g, we write it fg of x. That is basically f of x times g of x. And then if you have f over g of x, that is basically f of x divided by g of x, where g of x cannot be 0, because if it is, then it is undefined. So let's apply this to the example we have. Given that f of x equals 2x minus 3 and g of x is x plus 3, find each of the following. So we want to find f plus g of x, which is basically f of x plus g of x. So we take the first function, 2x minus 3, plus the second function, x plus 3, and then we combine like terms together. So the answer is going to be 2x plus x is 3x, and then negative 3 plus 3 is 0. So the final answer is just 3x. Next, f minus g of x is basically f of x minus g of x. So here, f of x is 2x minus 3 minus open parentheses, g of x is x plus 3. And here is where distributing the negative is very important. So we're going to have 2x minus 3 minus x minus 3. So if we combine these together, like terms, 2x minus x is x, negative 3 minus 3 is negative 6. So that is the final answer. Fg of x. Fg of x means f of x times g of x. So we have two binomials in this case, 2x minus 3 times x plus 3. We multiply in this manner. So first times first, first times last, last times first, last times last. And we have 2x times x is 2x squared. 2x times 3 is positive 6x. Negative 3 times x is negative 3x. And then negative 3 times 3 is negative 9. Now we combine like terms, which is basically the middle two terms together. So we will have 2x squared, positive 6x minus 3x is positive 3x minus 9. And that would be the final answer for the multiplication. For the division and its domain, because we need to find the domain, is equal to f of x over g of x. And we have to determine what x's are not acceptable in this case. So this is equal to 2x minus 3 over x plus 3. Notice I can notice immediately that negative 3 is not in the domain, so we can say such that x is not equal to negative 3. And that will be sufficient. And the domain in this case basically is from negative infinity to negative 3, x secluded, union from negative 3 to positive infinity. And then finally, we want to find, so in this case, since we have a number, we can basically say this is g of 2 over f of 2. G of 2 is basically 2 plus 3. We replaced the 2 in the expression x plus 2 over 2 times 2 minus 3. I replaced the 2 in the expression of f of x. So this is equal to 5 over 4 minus 3 is 1, which is equal to 5. So the final answer in this case is equal to 5. Definition: composition of functions. When the output of one function is used as the input of another, like the example we explained at the beginning, we call the entire operation a composition of a function. A composition of functions. For any input x and functions f and g, this action defines a composition function, which we write as f circle g. We read it f of g or f after g, such that f circle g of x is basically f of g of x. So g of x is going to be the domain of f of x. So the output of g of x will be the domain of f of x. The domain of the composition function f circle g or f after g is all x such that x is in the domain of g and g of x is in the domain of f. It is important to realize that the product of functions fg is not the same as the function composition. I have had many students say that, or when they solve equations like that, they basically multiply, which is not the correct action. F of g of x is not the same as f of x times g of x. Okay, so that is not true. Multiplication is not the same as composition. How to evaluate the function given a formula for a composition function? First, we evaluate the inside function using the input value or variable provided. Then we use the resulting output as the input of the outside function. Mainly, we evaluate from the inside out. So, for example, if you want to evaluate f of g of 1, we have to find g of 1 first. So we need to find g of 1 first and then use the answer as an input for the function f. So we need to find g of 1, which is basically 3 minus 1 equals 2. And then we need to find, so f of g of 1 is basically f of 2, because we found g of 1. So now f of 2 is basically 2 times 2 plus 1, which is equal to 5. So this answer is equal to 5. In a similar manner, we're going to find g of f of negative 2. So we're going to find f of negative 2 first, which is in this case equals 2 times negative 2 plus 1. That is negative 4 plus 1 equals negative 3. And then g of f of negative 2 is basically g of negative 3. So we're going to use the g function and replace each x with negative 3. So 3 minus negative 3, which is equal to 3 plus 3, that is equal to 6. If we want to find f of g of x, notice how we do not have a number here. So first, we're going to replace each x in the expression f of x with g of x. So f of g of x, meaning we're going to replace each x and put g of x instead in the first expression, which is in the first function, which is f of x. So in this case, I have g of x here. Now, I know what g of x is, so I'm going to replace g of x with its value or its formula, which is this one. So it's going to be 2 times, and then 3 minus x, so I replace g of x with its formula, plus 1. Now, all I need to do is the math. So I will distribute the 2 inside and combine like terms. So this is 6 minus 2x plus 1. I have 6 plus 1 is 7, so 7 minus 2x is the final answer here. And last but not least, I'm going to shrink all of that. Move it to the side. And now the last expression, I have g of f of x. G of f of x basically means we're going to write the function g of x, replacing each x with f of x. Now I know what f of x is, so 3 minus, and then I'm going to put f of x in between the parentheses, which is 2x plus 1. Now I'm going to distribute the negative, which is basically doing the math. So now I will have 3 minus 2x minus 1, which will be equal to 3 minus 1 is 2, so 2 minus 2x. And that will be the final answer for the third part. So hopefully the composition of function is clear using step-by-step here. How about if we were given a table? Using a table to evaluate a composition of function, when working with functions given as tables, we read input and output values from the table entries and always work from the inside to the outside, just like we did with the numbers. We evaluate the inside function first and then use the output of the inside function as the input of the outside function. For example, here is a table and we would like to evaluate f of g of 3. So f of g of 3, we're going to find g of 3 first. So g when x is equal to 3, here is g when x is equal to 3, the answer is 2. So we need g of 3 equals 2. Now we want to find f of g of 3, which means we want to find f of 2. So f of 2, so f when x is equal to 2 is equal to 8. So the final answer will be 8, which means this is going to be 8. G of f of 3. So we're going to find f of 3 first. So f of 3 is f when x is equal to 3. F when x is equal to 3 is 3. So we know that this is equal to 3. So that means g of f of 3 is basically g of 3. We computed that. So g of 3 is g when x is equal to 3. So here is g when x is equal to 3 is equal to 2. So the final answer will be 2. Hopefully that was clear as well. It takes a little bit of practice. Similar if you were given a graph and you would like to evaluate the composition function. So we have a graph of g of x. This is a graph of g of x. and this is a graph of f of x. And we would like to find f of g of 1. So we want to find g of 1 first. So we're going to use the first graph. We're going to use this graph right here to find g of 1. So g of 1 from the graph, so when x is equal to 1, I'm going to put a vertical line, and then at the intersection, I will draw a horizontal line to find the value. So g of 1 is equal to 3, which means if I want to find f of g of 1, I want to find f of 3, basically, because I found g of 1 is equal to 3. So I will go to the second graph, and I will determine f of 3. So when x is equal to 3, f of x, or f of 3 is equal to 4. So f of 3 is equal to 4, and that is basically the final answer for that question. I hope that composition of function is clear. One last note is composition of functions is not multiplication of functions. There is a big difference between the two, and I hope that you recognize that. If you need any assistance, please let me know.